This podcast is brought to you by LMU Munich.
Hi everyone, I would like to welcome you to the Alpha Room for some really great talks today, and I'm happy to introduce our first speaker, Valerio Maggio, and he's going to be talking about data formats for data science, which is a really excellent topic and becoming very popular these days.
Okay. Can you hear me? Okay, thanks. So first of all, thanks everybody for being here. I'm very excited of this new conference, actually. I'm going to talk about the data formats for data science in the next 30 minutes, more or less. Actually, this talk is a remastered version of one I gave. It's a remastered version of one I gave a few days ago in Budapest at the BI Forum conference, which was actually a remastered version of one talk, the same talk I gave at EuroPython this year. So actually, this version is going to be the director's confidential version, but I have included different jokes now. At Budapest, I've been told that actually this topic could not be probably the sexiest topic ever for big data or in data science in general, but it's quite useful. So at least I try to make it funny. Okay, so very few words about myself. I'm a postdoc researcher in FBK, in a research center in Italy, and I'm very interested in machine learning and deep learning. I'm a fellow Pythonista since 2006. I'm one of the chair of the PyData Italy event. We've had 2 events in the last couple of years, and we're going to have the next one the next year, so please check out PyData IT or PyData 8 on Twitter if you're interested, and it's going to be on April the next year in Florence again. So let's start talk about the main topic of this talk. So data science, as you know, it's about data, of course. And the first step in data science is loading and processing data. So in case you want to load the data, the first question you ask yourself is, what's the format in which data is saved? Because I need to know that to process the data properly. And in particular, since we're Python developers, what's the most Pythonic way to do it? In case you want to share your data and you want to store your results, for instance, probably the question is a bit different. The question now is, what's the best format to store the data and to share these data, actually? This topic is quite huge topic, and indeed you can even talk about reproducible science, which is a topic I'm very keen to, and it's very important. And the notebook, I think many of you here already know the Jupyter Notebook tool. It's a great tool, and it's sort of combination of data plus documentation. So in case you don't, please check that project out. Okay, so start with a very simple example. Talking about raw data, and in particular we're interested in data that just a bunch of numbers. Okay, so we want to process the data in this format. It's a very simple format, it's just textual format. I think that the most Pythonic way to do it, the very simple, the simplest idea we can come up with is just writing these few lines of code in Python. Okay, but this works, but of course it's not efficient because of matrix implemented as Python list, which is by far not efficient. So I think that in this particular case, NumPy to the rescue. NumPy ships with this function here, which is the loadtxt function that provides you out of the box a very simple way to process this kind of data. So textual data with just numbers in it. And returns you a NumPy array, which is by far more efficient than Python lists. Loadtxt has some additional parameters here. You may even specify delimiters or skip some rows here. The skip rows parameter. I'm sorry. But even better, NumPy has also this function which is gen from txt, which is basically the same function with but with more complicated behaviors in mind. So actually you have many more parameters to deal with many more cases in this case. In output you always have an NumPy array. In case you have raw data but some metadata on it, so labels on it, probably the comma separated value is the most famous and widely used and most widely adopted format in this particular case. So this is an example of CSV file, in case you don't know. In Python, in the standard library, we have the CSV module here. So this could be a very simple Pythonic way to process it, but indeed, in the PyData ecosystem, actually we have pandas. In case you don't know what pandas is, there's going to be a talk in this conference, actually, which is by Alexander Endorf, a friend of mine, who's going to talk about Introduction to Time Series with Pandas. It's a great talk, so please go for it. In more details, Pandas provides you out of the box this function, which is read CSV. That is basically devoted to read files or data in CSV files, and returns you in output a Pandas data frame. So actually this structure here is a Pandas data frame. If you come from the R community, you may be familiar with the data frame concept and data frame objects. In case you have more complicated version of the CSV files, for instance, in this case, you have the first 10 lines of metadata, not actual data. So to deal with these cases, read CSV has additional parameter here, which is skip rows. So you may skip the first 10 rows in this particular case and then get the data you're interested to. You may even do better with read CSV. It has lots of parameters to deal with many cases. So if you take a look at the documentation of read CSV, you're going to find definitely your use case to process this kind of data. In case you have data in spreadsheets, I don't know why you may have it, but probably, let's say somebody share with you these data, the data in these formats. From the data science perspective, we're not very interested into the, let's say, the charts into the file. We're just looking at the numbers here, the figures. In general, when I got to data share in this format, so basically that's my approach. But otherwise, I try to make compromises, and I look to Pandas in this case. Read Excel function is available in the Pandas package again. It's more or less the same, and even if in case you just needed to share your data in Excel format or you want to write it programmatically, there's this package in the Python ecosystem which is XLSX Writer that allows you to generate data in Excel format, and you can even do stuff quite a bit complicated than the basic ones. For instance, you may also add here, these examples have been gathered from the official documentation indeed. You can just add validations to cells where you just put the data in, so you can do even have the flexibility to do complicated stuff with the Excel format. Okay, that was for, let's say, textual data, but in case storage matters, probably binary format is a more appropriate way to store your data. In case you have lots of data and the storage spaces requirement you have, the binary format is indeed something you should look at. If you consider this representation of numbers in the native representation in the strings, for instance, you may realize that basically the number of bytes required to represent the numbers is by far different. Because in native representation the number of bytes is fixed, in strings of course it's not. So you may have very different storage requirements in case you basically store numbers in textual data as we showed in the very first example. Of course the space is not the only concern indeed. Speed also matters, and if you're going to process binary data is definitely faster than textual data. And in Python, the conversion to int and float is a bit slower, actually, because it's based on two slow functions here. But in general, the binary format is definitely an important thing to consider. In Python, we have Pickle, the package in the standard library, of course. We may just, for instance, pickle some NumPy array here. This is just an object of numbers, okay? So we're gonna write a binary file here with this directive, very simple to do, and we may also read it again, adding just a B in the end when in the mode of we open the file. So we may just write and read binary data, but in this particular case here, just the Pickle data, it's going to be unstructured binary, so it's a collection of binary chunks. Sometimes we may also need to add some structure to our data, but at the same time we want data to be storage friendly and to be in the binary format. So in this case, the HDF5 format could be definitely something very interesting. It's based on an open source file format specification. It works great with a tiny data set. That's because it's a binary format. It's storage friendly because it allows for compression, for instance, and it's also developer friendly because it ships with this query domain specific language to gather the data from the data files. And in Python we have many libraries here. We have PyDate tables, HDF5 and H5Py libraries. Just an example, I can tell you that for those of you who know what Keras is, actually Keras is a library for deep learning. Out of the box, Keras provides you these two functions to deep learning models to save and load weights, and these weights are saved in HDF5 because of the complex structure they may have in the case of neural networks. Just very quick examples on how HDF5 works. So using this library here, H5Py, you may create this file, which is in binary format out of the box. You may create a data set, so this file is going to be organized in multiple data sets, and this organization could be also hierarchical. So in this case, you can just include inside the data set an NumPy array automatically. So, and you can also manage these dataset object here as a classic structure you can slice upon. So you just a NumPy array, as it was just a NumPy array, but actually it's a binary object. As you may notice, it has native and tight integration with NumPy. This is another package here. This is PyTables. So actually here we're creating a new table here. And we want to access the table just with dot notation, so it's just objects. And so basically the levels of hierarchy we having in this data set here is just the number of dots we're using to access the data. In case we want to specify explicitly the group, we have this function here, which is create group. So in this case, we have the original data set, so the root of the, you have to think of it just a tree of data organized in multiple levels. So in case here we're basically adding a new group, and so we have the second level, and we're basically defining a sort of path to access the data, and we may leverage on this path to access the data. So here we're creating another data set with this path, so the second level here, and so we may just access the data using the path we defined. That's very nice. And it's a sort of dictionary access here, but we're basically navigating through the binary format. Another very nice feature this format has is the data chunking feature, and this is quite useful in case you want to distribute your data among multiple machines, for instance. In case of having this internal representation, so as a continuous data set, you may also have these data sets represented as chunks, and it's quite easy to do that. You basically specify the size of the chunk here, and this is actually going to be the internal representation of data. But in case you want to deal with this data, the library tells you, allows you to do it in a very simple way, without worrying about the fact that the data are spread among chunks. This is an example using the MPI library for parallel processing. So here we're basically creating a new data set in chunks, and with these chunks here, and we're basically distributing the storage of these data among multiple machines. So it's very easy to use and very effective. In case you're coming from the particle physics domain, but in general, this is quite interesting to talk about. It's the root data format. I don't know if you guys know what root is. Actually, root is a combination of tool and a data format as well. Root is a data analysis framework developed by the CERN Center. It's written natively in C++, but as out-of-the-box provides out-of-the-box an extension for Python. This is called PyRoot. Indeed, the Root 6 version, which is the latest version of Root, also ships with a Jupyter kernel, so you're able also to do it inside your browser now. root defines this new binary data format, which is based on a serialization of C++ object. And because in this particular domain, I mean the particle physics domain, speed and storage matters. Indeed, the root data format is expected to deal with a huge amount of data. This is an example of how root is. So basically, root provides this sort of interactive interpreter when you can write your C++-ish style. And you got these graphical user interface to navigate your data, organized again as a tree of objects, binary object inside, and then you can just plot histograms. So that's the main objective of root, most of the use cases. This is the C++ version, of course, so the C++ style inside the root interactive shell, how you can just deal with root data format. And this is the Python PyRoot, which is a sort of, I call it Pythonish style, because it's actually, it's Python, of course, so it's by far shorter. But here you have, even in the name of the object here, is very C++ style, okay? Luckily for us, there's these two couple of projects now developing, which are RootPy and RootNumPy, definitely nice projects that tries to integrate the root data format in a very Pythonic way. This is an example, for instance. Here you basically opening a file here. This is the PyRoot approach here, the same of the previous example, but now that's the RootPy approach. So, sorry for the mess, actually it's PyRoot versus RootPy, it's sort of a mess, but the RootPy is the Pythonic style. So you open the file here, and you're basically plotting the 2D histogram, okay, with this object here, and you draw it without doing any of these weird stuff here. Basically here you're drawing an histogram and you're redirecting the output of the draw into a new C++ object, which is quite weird. But here you have a parameter to do that. It's very, it's by far more clean as an API. An example of RootNumPy actually, RootNumPy has this function which is rootArray, which is a function that is expected to read a root file and returns you back a NumPy array, which is most of the time very useful because in general, if you want to get the data from root file, actually you're supposed to draw an histogram before and then you got the data. It's quite weird. In this case, you're not allowed, you're not required anymore to draw your histogram. And moreover, it has a very tight integration with PyRoot object. So actually, here you're using RootPy to fill an histogram using a PyRoot object, okay? So the histogram here is the old, let's say, PyRoot object, and you fill it using a RootPy object. So it's very, quite good integrated. And finally, this package also ships with this tool inside, which is root2HDF5, so you can just convert more or less automatically without any pain the root file format into the HDF5 format, in case you want to process your data with different libraries than these ones. Being, again, in the domain of binary formats, in case you have, for instance, the case could be geographical data, and NetCDF is one of the most used format in this case. In case you have a multi-dimensional array and you want to put labels on these arrays, Pandas is not enough, because Pandas has a 2D approach. So the Xarray comes to the rescue. Actually, Xarray develops this new object here, which is DataArray. It's just this slide, so it's just to give you the reference to this project. It's quite nice. Actually, in case you have these requirements, so you have multiple data in multiple dimensions, for instance, anyway, any dimensions in terms of the tensor data you have, and you want to put labels on each of the dimension you have, Xarray is the way to go, okay? In case you have relational databases, and the relational databases are quite focused on the information architecture, so the idea here is to have normalized information, so no duplicates in the fixed structure. We have the SQL, as you know, it's quite standard approach to query the data from the database. And but the problem in this case is that the dialect of this SQL can change among the different vendors. So in case you want to write SQL statement for Oracle database, it's slightly different from the one you write for PostgreSQL or MySQL. Okay. So actually accessing the data using very raw SQL is not very portable. So in this case, I highly suggest you to go for the RM way, so the object relational mapper way. In Python, to do that, we have this quite famous package, which is SQL Alchemy, that has this approach. So basically, it's a very object-oriented approach. It basically provides a way to separate the actual data in the database to the business layer, so the object and the classes you do to deal with the data, and automatically it provides this DB API, so the API to gather the data from in a very object-oriented way. And also it allows you to leverage on multiple drivers you may have on your machine to interact with the database and to deal with the different dialects you may have according to the specific database management system. This is an example. For instance, you may see the same Python instruction here just to deal with databases stored into SQLite rather than PostgreSQL. And here you may also use different formats, different drivers connecting to the database, in this particular case, PostgreSQL. Otherwise, you may also deal with it in a very object-oriented way. In this particular case, I'm creating this user class, which is going to be my table in the database. I'm basically required just to extend this base class here, imported from SQL Alchemy. Then I'm defining here the columns of my table just as Python attributes of the objects. And then I'm finally able to create a session here and add all these instances of new objects in the database. So these instructions here are automatically converted by SQL Alchemy into insert statements in SQL, and the SQL that has been generated is definitely compliant with the engine I'm connected to. So in the proper dialect the engine expects to. In case our focus is not more into the structure, but we require flexibility on our data, so the structure is not fixed yet, probably the JSON-based data format and the well-known NoSQL database are the solution. In Python, for instance, we have MongoDB, it's one of the most famous ones, and in Python we have PyMongo. Indeed, the JSON format is quite famous format. It's a collection of JavaScript objects, basically. And in case you don't know, actually JSON is the format of choice for Jupyter notebooks. Inside the notebook files are just JSON files. In case you want flexibility and also a sort of validation, but you want to validate your structure, probably XML-based data format is the one they may suggest you, but actually this is all I have to do and to say about XML. Most importantly, in case you have the speed requirement, especially in case you want to do data science inside the database, there are these new kind of technologies that are called column-oriented database. They're very nice to and very interesting technology. They're super effective inside database analytics. So far we have two different categories of these kind of databases. The one based on NoSQL approach and the other one based on SQL approach, so are more relational database oriented. The difference with these kind of technologies is that they change the perspective of the data. So basically data are no more stored into rows, in a row-based perspective, but rather in a column-oriented perspective. So it's basically a transposition of the data you have. I'm going to show you examples from this database here. It's MongoDB database. Basically, you have a tight integration with Python Word. Actually, each data type is automatically mapped to NumPy data type, which is going to be very effective. And in case here you're basically creating the functions in a sort of SQL language. So you're creating function that's supposed to run inside the database, but you're specifying that Python is going to be the language you're going to use. So here it's just Python code that's expected to run inside the database. To see a more practical example here, so here we have two functions. creating tables. So actually we expect to return table as a result. In this case, we're basically returning a confusion matrix from some data collected in input as parameters. And basically data input to these functions will be NumPy arrays of this data type. So basically columns in our query. Okay, here we're creating a confusion matrix, and then we're creating another table with other statistics, just like accuracy, precision, or whatever. Here, the sensitivity, specificity. And then, after that, we're going to use these two functions inside a query. So basically, we provide the data and we execute the functions, providing the data from a query, actually. Okay? In case you have questions on this, I'm definitely many things to say to you. Finally, the last use case I'm going to talk to you about is when you have data in multiple formats. One approach is to go for this big data lake. So actually, when you talk about the data lake, you talk about HDFS. In case you don't know, HDFS is the data format specified by the Hadoop word, and the Hadoop word is basically connected to everything is about big data, more or less, okay? This is actually my approach when I got to be working with Java stuff. So I try to feign, and more or less, because I don't really like Java. But indeed, I'm going to show you an example of this nice library, which is called HDFS3. These examples have been gathered from this link here. You may find the reference in the slide. So this is just a snapshot and excerpt of the example. This is just to show you how a CSV file stored on the HDFS file system it can be used inside Python code. Here we're basically opening with this library here. We may navigate the file system and open the file on the CSV on a single file on the HDF file system. We read this CSV using pandas, okay, and we basically got with the data frame we expected. But most importantly, when we want to collect a wildcard of CSV files on the HDFS file system, we want to execute this even on multiple machines because data can be spread among different machines. So this library provides us the way to do it in a distributed fashion. And we again read the CSV file as using the HDFS library, and then we store it as pandas data frame as we expected. Here the pandas data frame also has the column here, so we collected perfectly all the data we have. And finally, that's basically this sort of head in information here. So we're also processing the data with the assign function here is just to further processing this, so we're filtering the columns of the data we want to collect from the CSV file. The nice thing about this library is that there is no Java along the way. It's just a C++ implementation of the specification of the HDFS format. So actually the last example is this one, talking about the Blaze project. The Blaze project is a nice project, and the approach of the Blaze project is you may have multiple formats with a unique interface. Actually, Blaze defines this object here, which is the data object, and the data object expects you to be anything you may have. For instance, a relational database, in this case it's a SQLite database, but the data object will also be a CSV file or a textual file, whatever you want. And basically, Blaze provides you this data object that is a sort of unique interface, unique API to deal with the data, regardless which is the format you have. And this is also useful to take a look, even if you have to do something which is called out-of-core processing. So if you have distributed computation of your data. So, of course, there are many, many formats I left behind, and that's because of many requirements. I basically collected those according to the requirements that comes to my mind and my everyday job. But the important takeaway I would say is just like complicated data require complicated formats, and complicated formats require good tools. At least in Python we have many actually, and we basically are striving to do even better in the PyData ecosystem. And that's it basically. So thanks a lot for your kind attention.
I would like to thank Valeria for a great talk, and it's time for a coffee break now.